I realized yesterday that I gave you a bunch of problems, but I really didn't give you some samples, and you guys did really good, but I should probably do some sample questions. I do have this one here. Let's maybe, it's not up on the screen there, but let's have a look at this one here. Calculating work done in various situations. So basically this is when are we doing work and when are we not doing work. And you'll find out that just like Friday afternoons, sometimes there's not a lot of work happening.
Same as Monday morning.
Yeah, exactly. So, case number one, a force acts on a mass and accelerates along a frictionless surface. Or if friction is present, the object might just move along at a constant velocity. Either case, the energy is transferred to the mass, work is done by the force, and it can be calculated using W equals Ft. Where does that work go? If we've got like 50 joules of work, where does it get transferred? What does it become? Energy of?
Energy.
You might remember probably from about grade 6, I think, maybe.
Oh.
Kinetic energy? I don't even know where that is first introduced, kinetic energy. Most kids know that kinetic energy is energy in motion, though.
Probably not grade 6.
Maybe not grade 6? I'm not sure.
Yeah, I didn't do physics.
What if there is friction present? Well, then it's energy of motion, and there's also some heat energy, right? And there might be some sound as well. In any case, W equals Ft. But consider motion at a constant velocity across a frictionless surface. Once the object is moving, no force is required to maintain the motion, thus W equals Fd. No force, 0. You get work is also equal to 0, no work done. So there has to be a force, there has to be motion for there to be work. And if there's work, it's got to be transferred to either kinetic energy or potential energy or heat energy or some other kind of energy. When you eat your bowl of Cheerios in the morning, you're ingesting energy. Where does it go? Your body converts it to energy that you can use for moving around or for breathing or for whatever you do during your day. And again, as I said yesterday, if that energy isn't used up, it gets stored. Case number 2, when an object is lifted vertically, work is done against the force of gravity. The work needed is equal to the weight of the object is equal to mg, and the work done there's a little blank. What should you fill in there? I think it's mgd. Or I think yesterday we went with the work done here. Whoops. Right? The force is the weight force, and that is mgd, sometimes written as mgh for height, because it's a vertical distance height.
Right.
Okay? So in that little space there where it says, therefore, work done, you would write equal to Ft. What force is it? Weight force. How do we find weight force? M times G times the D, sometimes an H. Again, work is transferred here. What kind of energy does it become at when it's transferred, put up on a shelf like that? Potential energy. Gravitational potential energy.
So what's kinetic then? That's just moving.
Kinetic is when it's moving. We will derive a formula for kinetic energy in the very near future.
Alright.
1/2 mv squared. What if, in case 3, the object is tied down, can't move? So the force there is pulling that mass, but it's tied to that big gray block. Is there any motion? No, you can pull for all your work. Doesn't matter how much you pull, the D is still 0, work done, 0. What about someone sitting on a pole? Liam is sitting up there on the tree in musical. He's a mass, he's sitting on something. Is there any motion? No work done, just sitting there, has to be motion. What about the bald, skinny man carrying a briefcase extended with his arm extended? That's not a picture of me, Riley, I know what you're thinking. He's looks like a what?
A purse.
Yes, a bald, skinny man carrying a purse with his arm straight up like this. Is there any work done? No work done. How come, Caleb? It's moving. But is there any, how much potential energy here? 1.5 meters worth. Same thing over here, right? Looks just like the picture. Bald skinny guy walking across the floor. No work done. Is there work done at the start? Like right now it's at 0. if I accelerate it, right, I have to give it applied force to accelerate it from 0 to some motion. So a little bit of work done at the start, a little bit of work done at the end when I slow down. But other than that, no work done. Flip the page over.
Just like not really care about that.
Yeah. What about if it's in uniform circular motion? Okay, now, after 5 revolutions, 10 revolutions, etc., the body has the same velocity, hence a constant amount of energy. Thus, we conclude that the centripetal force does no work. So there is force and there is motion, but there's no work. How come? Because there was no change in velocity. There was no energy transfer. Thus, we conclude that centripetal force does no work. In general, and you might want to highlight this, there is no energy transfer, no work done when a force is exerted on a body perpendicular to the direction of its motion. So the F and the D have to be not only existent, but they have to be in the same direction. In this case here, the force is towards the center, but the velocity is tangent, not in the same direction, no work done. That's on the back, right there. No work done. Again, it's like Monday morning, as Steve says. Not a lot of work getting done. What about force exerted at an angle? Maybe pulling on a wagon or a sled. You pull in the direction of F, but the object moves horizontally in the direction of here they listed as Fx. We know it as Fh usually, right? F can be broken down into 2 components. What's that F upside down key thing?
Perpendicular.
Perpendicular. And Fx. It should probably read Fy and Fx. We would know Fy as Fv, vertical, and Fx would be Fh. Good. So, what is Fv? It's going to be F sine theta. Is there any vertical work done as you drag that sled across the floor? No. So there's no vertical work. Is there any horizontal work? Yes, there is. It's Fd cos theta. Why Fd cos theta? At the bottom there. It's kind of in bold. Work done is Fd. In this case, it's the horizontal component. So it's going to be F cos theta d, which I guess you could say is the same thing as Fd cos theta. All some sort of things to keep in mind as we move forward to some sample questions. Pretty exciting stuff. Okay. Let's start with sample question. Probably an easy one. Let's hope. How much work is done when sliding a 30 kilogram chair a distance of 15 meters across a rough surface where the force of friction is 50 newtons? Let's just draw a quick picture. I know the size is not very big there, but I think we should have enough room. We do not know how much the applied force is, do we? Is there any acceleration happening here? The unit for work is the joule. Same as energy. Mass is 30. Yeah, I got an FF of minus 50 there. Is there any acceleration? If there was, they'd have to tell it to us, right? I think we're going to have to assume here that the FA is equal to the FF.
So why do
I think it's just W equals FD. What's that, Hannah?
so why do we assume that?
Well, it doesn't say with an acceleration of 2 or anything like that, right? It doesn't ask us for an acceleration. There's no applied force. You're going to have to make that assumption. I think it's just 50 times 15. Does the 30 kilograms matter? The force of friction is given. Usually, certainly for grade 12s, mu is FF over Fn. The mass would come into play there. We've already gotten FF. In other words, they've taken mu, they've taken mg is equal to Fn, they've taken all that for you, they've given it to you as FF. I think it's just 50 times 15. What's that, 750? It's the first one, it's pretty easy. 750. Oh yes, 750 joules, thank you. My mistake. I wish I'd made that mistake on purpose, because it would have been a good one to make on purpose, but I didn't. What about work done against gravity? How much work is done lifting 2 bricks, each of mass 1.4 kilos, from the floor to the top of your table at a distance of 80 centimeters? Okay, there's a couple of wrinkles here, right? Combine the masses, right? .8 kilos. Make sure your distance is in meters. Weight force, applied force. The applied force is equal to the weight force, right? Mass times gravity. 2.8 times 9.8. $27.44. Are you going to need a little bit more force than that to get the bricks moving?
Yeah.
But once you do, then you just have to balance FW, right?
Not why we don't really care about it.
Yeah. It's just to get it up to speed, right? I mean, could we? Yeah. Would it mess up our calculations? Yes. So, I mean, we're simplifying things here, right?
I just didn't see this.
Oh yeah, because we're trying to figure out the work, so the distance does matter. So now it's work equals FD. We could use MGD if we wanted. We could just do it in 2 steps like this, make it like a country song. Oh, you like that one, did you? 22.0, I guess. 21.95 joules. How much potential energy do these 2 bricks have now? 21.95 joules. If you let them go, they would have kinetic energy, 21.95 joules of kinetic energy. It's pretty easy, isn't it? Is this easier than the circular motion stuff? Oh yeah, it's a nice little breather. Is it going to get harder? Yeah, a little bit. No, we got to do momentum too. That one's... Although I find that since I've moved it to the end of the course, people have done a lot better on it. Maybe that might be why. Okay. Is this example 3? Is it all on the front page there?
Yeah.
Okay. 1.5 kilogram dynamics cart pulled at an angle of 30 degrees with the horizontal with a force of 25 newtons. Cart moves 4 meters. How much work is done? Are you starting to see all the similarities in the problems, how they all sort of fit together? I think so, right? You see the same things over and over again, right? 30 degrees. Here's F. H. Do you just now know, okay, I got to find the horizontal component, right? FH is going to be F cos theta. 25 times the cosine of 30. $21.7. How much work am I going to need to pull up the plane? Well, this is a sort of a subset of work against gravity, because here, how much applied force do you need? Like, what do you have to balance? Why do you need force to pull it up that ramp? Like, what's opposing it? FD, right? The component of gravity that acts down the plane. So, the applied force is equal to the force down the plane, which is mg sine theta. 30 kilos times 9.8 times the sine of 30 degrees. 147 newtons. And that's equal to the FA, assuming that it moves up at a constant speed, right? How much work done? F times D, 147 times 6, 882 joules. Okay, that's pretty straightforward. What if I just use my muscles and just lift it straight up? The work done
It's the same.
would be the weight force times the D, mgd, mgh if you prefer, 30, 9.8, a distance of 3. What is it, Ryan? You said it already. It's the same, is it not? Within a rounding error?
I didn't say it was the same.
Oh, I thought it was you. Oh, that was you, Jason? Sorry. It's the same. What the heck? Is that just coincidence, or is it supposed to be like that? Supposed to be. How come? How much potential energy does it have sitting up there? The same amount, whether you pushed it up the ramp or lifted it straight up or whatever. However it got there, that's how much potential energy it has, and that's how much work was done. So it shouldn't be surprising. Okay, now what is the trade-off? Well, how much force did you need here? Only 147. How much force are you going to need here? 30 times 9.8, a little less than 300, right? It takes more force. The trade-off is you don't have to do it for as long. But what if there's 50 newtons of friction up the plane? What changes? Well, this part changes, right? Part C. Now I'm going to write F REQ, or F net, I guess. Really, I guess it's F net. If there's 50 newtons of friction, right, I'm going to need my FD, my 147, up the ramp, plus another 50 newtons to compensate for friction.
What did you have D and
The net force now,
wouldn't our wait?
go ahead.
Wouldn't our F net be 147 and our friction be negative, and then you move it over, and then FD would equal that number? Because you have a positive. What's the FD and F in the same direction?
Yeah.
FD.
Yeah. Let's.
Oh, no.
Yeah, it's okay. It's okay.
Which question's A and which one's B?
Oh, sorry. This is A here. These two here are A.
The two are A?
Yeah. This is B. Okay, I see what's causing Jason some grief here. Okay, let me redraw this free body diagram. Okay. So we got FA up, we got FD down, and FF like this, right? So just draw it. That's good. Thanks. So the net force, I guess you really should say, is the FA plus the FD plus the FF. I think this will make sense for it. Can we say down the plane is negative? Can we assign that to be negative? Okay. So FA, FD is going to be minus 147 down. FF is minus 50. What is the net force? 0, because there's no acceleration. And so what you end up here, Jason, with is minus FA is equal to minus 197, or FA is 197. So I'm just adding the FD in, okay? I was kind of glossing over some of the details a little bit. Yeah, okay, that's fine.
So because that's going down, it's negative?
Yeah, we're assigning it to be negative. We're declaring down the ramp to be negative. Exactly, Zach. Why 6? Because that's the distance that it actually travels, right? Is it gonna be more? Well, sure, look at this was times 6 here. So now instead of 147, it's 197 times 6. 1182. Did the block all of a sudden gain more potential energy because there's some friction? No. Where did the extra energy go? Heat. It goes into heat. Okay, there's always going to be some energy loss. You know, they say conservation of energy. I mean, is the energy conserved? Sure. Potential energy, heat energy. But generally, heat energy just goes poof into the wind, right? Gone. Disappears. Has that given you a better feeling for trying some problems now?
So you did more work, but it was still the same outcome as the last.
Yeah. You did more work, but because some of that work was done against friction, it's lost to heat energy, right? And the greater the amount of heat energy, the less efficient.
Right here, what would be able to, like, I guess, how much heat energy is lost?
Yeah, how much, that's a great question, Zach. Could we do that right now?
If we do what? Oh, I guess it's...
What would the heat be? It would just be 182 minus 882. How much is that? Good question.
Well, under 2, 3.
300. Which would just be what? 50 newtons times 6, right? I'm losing it this afternoon. Just not having my A game, you guys. In fact, there are ovens like that one back there. I've never actually used it, but Mr. Wally, who I know subs occasionally, you guys may know him. I know you can put, that oven is designed to put food in, and you figure out how much heat it gives off as you burn it, and it tells you the calorie content of the food.
Oh, can we do that?
I don't know how to do it.
Oh, figure it out. Let's learn.
Yeah.
Maybe
Experiment with it. Figure out how to do it.
I'll give it, I don't even know if it works.
You just go,